Okay, gentlemen, we are now going to look at 5.5, where we will be solving some equations and inequalities that involve logs and our exponents. So if we just recall back, anytime we had two quantities that were equal to each other and they had the exact same base, then we know that then those two exponents we could set equal to each other, and that's where we would get our x equal to y. Same idea would be true with our log expressions. If we have two log quantities that are equal to each other, and both of those log quantities have the exact same base, then that quantity C would have to equal that quantity of D. So those will come in handy as we are going through and solving some of our equations here. So let's start with number one. Number one, we have a couple of different options. Okay, we know that if we have a number in front of a log, recall that multiplication, that means that that coefficient in front of that log could have been up here as an exponent. So I'm going to move that 2 back up as an exponent so that the log of x plus 1 is equal to the log of x minus 1 quantity squared. And now, if that is the case, we are right here where we have two log expressions equal to each other. Both are of base b, and if that is the case, then we can say that x plus 1 must equal x minus 1 quantity squared. And now we're back to just our normal, regular solving equations. So if I multiply that out, x plus 1 is equal to x squared minus 2x plus 1. We have a quadratic. We're going to set that equal to 0. So x squared minus 3x, our 1's will cancel out. Factoring out our x and using zero product property, we initially are going to get x equal to 0 and x equal to 3. But we also know anytime we're working with logs, we need to be very careful about domain because we do have a restrictive domain. With the log quantity of x plus 1, we know that x plus 1 has to be greater than 0, which means we can only use values of x greater than a negative 1. And from this log quantity, we know that x minus 1 needs to be greater than 0, so we can only use values of x greater than a positive 1. We need to make sure that both log expressions are being met. So our overall domain is that we can only use values of x that are greater than 1. So therefore, x cannot be 0 because then that would give us a negative log quantity for that term on the right. So our final solution is only x equal to 3. If we look at number 2, on the left side, we have addition of two different logs. And we know that when we are adding logs, when we are adding exponents, that means that multiplication with a common base was going on. So on the left side, we could think of that as the log of 2x plus 4 times the quantity of x minus 2 equal to 1. I'm going to FOIL that out inside the bracket. So we're going to have a 2x squared, a minus 4x, a plus 4x, and a minus 8 equal to 1, or the log of 2x squared minus 8, combining like terms, equal to 1. And now we are back to where we are looking at a log form, and we can switch this to an exponential form. And recall, if there is no base that is written, a base 10 is implied. So if I switch that to exponential form, that base 10 logs are equal to exponents. The exponent is the 1, so 10 to the first is equal to the 2x squared minus 8. Or if we go to solve, I'm just going to come up here, we get 18 is equal to 2x squared. X squared is equal to 9. or x is equal to plus or minus 3. Taking the square root, recall your absolute values, and that's where the plus minus is coming from. But again, recall with our logs, we also have a restrictive domain, so we do need to check our domain for our quantities. We know that the quantity of 2x plus 4 has to be greater than 0, which means that x would have to be greater than a negative 2. And we also have the quantity of x minus 2. That must be greater than 0, which means x has to be greater than a positive 2. So to make sure that both are being met, we can only use values of x that are greater than 2, which means that the x equal to a negative 3 is not an option, and our final answer is just x equal to a positive 3. On number 3, we are looking at a log form, and we can switch this to an exponential form. We have a base of 2. Remember that logs equal exponents, so that base of 2 is being raised to an exponent of a negative 1, which is equal to this quantity of log of x base 3. And we know 2 to the negative 1 is just 1/2. And now again, we are looking at another log form, which means we can switch this to an exponential form. Our base was the 3, and we know that logs equal exponents. So the exponent is the 1/2, so 3 to the 1/2 is equal to x, or x is equal to the square root of 3. On number 4, we have 10 to the 2x plus 3 times 10 to the x minus 10 equal to 0. And recall, if you have multiplication of exponents going on, that means that you could have had a power raised to a power. So I can think of that first term as 10 to the x being squared plus 3 times 10 to the x minus 10 equal 0. And we have this repetitive quantity, so I could think of that is the exact same thing as just something similar to an a squared plus 3 times a minus 10, if I wanted to make a temporary substitution for this 10 to the x quantity being our a. And we know that a squared plus 3a minus 10 is a quick factor of an a plus 5, a minus 2, 0 product property giving us a equal to a negative 5 and a positive 2. But it wasn't a, it was this 10 to the x quantity that we were solving for. So 10 to the x would be equal to the negative 5, or 10 to the x would equal the positive 2. And on this left side, we know that 10 to the x is never going to equal a negative 5. Remember, you have that horizontal asymptote at y equal to 0. So this one is not going to happen. 10 to the x equaling 2, I am looking at an exponential form. I can put this in a log form. Our base is the 10. Logs equal the exponents. So we are looking at the log of 2 base 10 equaling to that exponent of x. So our final answer is just that log of 2 base 10. And you do not need to write the 10. You could just put log of 2. That base 10 is implied. On number 5, we are solving for x. We have the log of x cubed equaling 3 times the natural log of x. And keep in mind that when we have this power, I could bring that down if I wanted to, or if I wanted to, I could have taken this coefficient and brought it up. Either way, both are correct. I am just going to put those both as 3 natural log of x equaling 3 natural log of x, or we just have the natural log of x equaling the natural log of x, which is always going to be true for all values in our domain. And recall with logs, we do have a restrictive domain. We can only take logs of positive quantities. We cannot take logs of zeros or negatives. So this is true for all values that are greater than 0. So from 0 to infinity, not including our 0. On 6, now keep in mind it is the entire quantity that is being cubed, where on 5 it was only the x that was being cubed. So on 6, I could think of this if I wanted to make a temporary substitution, and I'm just going to let my natural log of x equal a. This is the same thing as a cubed equaling 3a, or a cubed minus 3a equal to 0 if you wanted to make a temporary substitution, if you're not liking those log terms. And if I just factor out my a, I know that either a is going to equal 0 or a squared is going to equal 3, which means a is going to equal plus or minus root 3 using zero product property and taking the square root of both sides on that right quantity term. But we weren't solving for a. I made a temporary substitution, and my a was equivalent to the natural log of x. So if we go and finish that off, then we really have the natural log of x that is equal to 0, and the natural log of x that is equal to plus or minus root 3. Both of those are in a log form. We can switch those to an exponential form, where then this is just e raised to the 0 power, giving us x. And we know e to the 0 is just 1. So this is x equal to 1. And this is e raised to the plus or minus root 3 is equal to x. And there are our 3 solutions, which we know there should be 3, for our x quantity. If we look at number 7, on number 7, we want to solve for x. We have a term in our denominator that involves x, and we need to get that out of the denominator. So I'm going to multiply both sides by the natural log of x. On the left side, I'm going to distribute that quantity, which would give us the natural log of x times the natural log of 4 minus the natural log of x quantity squared equaling the natural log of 4, because our natural log of x's would cancel on the right side. If I set that equal to 0, I'm going to have the natural log of x quantity squared minus natural log of 4 natural log of x plus the natural log of 4. Where again, if you're not liking all those log terms, this is a repetitive quantity, and if I want, I can just temporarily call my natural log of x an a, where I'm really just looking at 0 equaling a squared minus natural log of 4a plus natural log of 4. Remember, natural log of 4 is just a number. A little bit bigger than 1, not quite as big as 2. And now here I have a quadratic, and I know factoring sometimes works. Quadratic formula will always work. So if I go to solve for A, I know that A, I'm going to come over here to the left here, that A would equal minus B, so that would be my positive natural log of 4, plus or minus the square root of B squared, so minus natural log of 4 quantity squared, minus 4, A is 1, the coefficient of our square term is 1, times our C, which is natural log of 4, all divided by 2 times A. So in this case, 2 times 1. And so we have A is equal to the natural log of 4 plus or minus the natural log of 4 quantity squared minus 4 natural log of 4, all divided by 2. And if we think about this for a second, natural log of 4, well, natural log of 4 is a base e. And so e to what exponent, or 2.7 to what exponent, gives us 4. That's a little bit bigger than 1. So on this particular term, we have something a little bit bigger than 1 being squared, versus here on this term, we have 4 times 1 point something. And so since we are subtracting these quantities here, we are actually going to end up with a negative number inside of our radical. And with the reals, we can't have a negative inside our radical, so therefore there is no solution here with the reals. Okay. Also, another thing to note on this problem, gentlemen, is on the left side, keep in mind the left and the right are two totally different quantities. On the left side, if you had wanted to rewrite that 2 log subtraction, you could have thought of that as the natural log is 2 log subtraction is 1 log division, so that would be the natural log of 4 divided by x, versus the right side, 2 log division, log quantity divided by a log quantity. If I wanted to rewrite the right side of that equation, that actually is a base change, which is the natural log, that is, erase that, that is actually the log of 4 base x, if you were to rewrite those. So those are 2 totally different quantities. Just keep in mind they are not the same. Okay? On 8, we have this 2, that is this coefficient of this log, the 2 that is out in front. So keep in mind that I can take that 2 and I can bring that 2 up as an exponent. And so the left side, the natural log of 3x squared, is equal to the natural log of the quantity 3x squared. And now I'm back to, I have 2 log quantities that are equal to each other. Both of these are base e implied, which means that this 3x squared quantity has to equal this 3x quantity. Our bases are the same, our exponents are equal, then those quantities have to be equal to each other. Or we really have 3x squared is equal to 9x squared, or 0 is equal to 6x squared, combining like terms, or 0 is equal to x squared dividing by 6, and we get x equal to 0. But we know with logs, we have a restrictive domain. We cannot take logs of 0 or negative numbers, so therefore here we also have no solution. I'm going to let you try number 9 with your e to the x and try to solve that doing x. And we will do one more over here on number 10. So we had just talked about if we had two quantities that were equal to each other and the bases are the same, then we know that the exponents have to be equal to each other. Well, in terms of inequalities, that same thought process, if p is smaller than q, then if I have a base raised to a smaller exponent, less than that same base raised to the bigger exponent, we know that this side would have to be smaller than this side. Likewise, the same statement is true with our logs. We know if we had two log quantities equal to each other, both same base, then those quantities would have to be equal to each other. Well, the same idea is true. If the p quantity is smaller than the q quantity, then the log of that p quantity has to be smaller than the log of the q quantity if they are the same bases. So keeping all of those and now just working with inequalities instead of an equal sign, just switching it to an inequality. We know we still have to isolate that x variable. So the first thing I'm going to do is I'm going to bring over that x to try to isolate my x quantity. So I'm going to divide out my 6, making that 5 minus 1.6 to the x, which is greater than or equal to 13.6. I'm going to bring over my 5. And we know subtracting 5 is really the same thing as subtracting 36. So I am really just looking at a negative 17.6, if I am subtracting correctly here. And I can divide both sides by a negative 1. But recall, really, the one main rule you got to remember with inequalities is anytime you multiply or divide both sides by a negative number, we are going to need to switch that inequality sign. So we really have 1.6 to the x less than or equal to 17.6. And now, in order to solve for our unknown, which is in the exponent position, I'm going to, just like I can add 5 to both sides, I can divide 7 by both sides, I can subtract 3 from both sides. Whatever I do to the left, I need to do to the right. So I'm going to take the log of both sides, and I'm just going to work with log base 10. So I'm going to take the log of 1.6 to the x less than or equal to the log of 17.6. If the left side is smaller than the right side, then the log of that quantity on the left is going to be smaller than or equal to the log of that quantity on the right. Going right back up to over here. Okay. And now we know that if we have the log of a quantity raised to a power, I can take that power and I can bring it down in front as a coefficient, and I'm actually just going to come up here. So we're really going to have x times the log of 1.6 less than or equal to the log of 17.6. And in order to solve, I just need to divide both sides by the log of 1.6. And keep in mind, the one rule with inequalities is if you multiply or divide both sides by a negative number, you need to switch the inequality. Well, the log of 1.6, keep in mind with your log graph, the log of 1 is 0. Remember, this is the point, 1, 0. So the log of anything larger than 1 is going to be a positive number. The log of anything between 0 and 1 is going to be a negative number. So the log of 1.6, we are dividing by something positive. So we do not need to worry about switching our inequality sign. And we're looking at the log of 17.6 divided by the log of 1.6. And that would be our final answer. And keep in mind, you cannot just divide those numbers. If you were to switch that, our answer right now is in terms of base 10. This is also equivalent because we do have a base change going on. This is also equivalent to the log of 17.6 base 1.6. So those say the same thing. Okay? And that is 5.5.